Now you need to be careful here that H1, so for that, H1 is positive, H2 is negative with respect to my selection of this frame. At the final instant, when it's going to be horizontal, then H1 will be equal to H2, which is going to be equal to 0. So you can make a calculation of the potential energy at the first instant as M1 G H1, the total energy we are talking about. So there should be a minus M2 G H2. Now the reason of the minus sign is because H2 is a minus distance from the O point, minus length from the O point. Okay. So at that instant, there is no other source of energy, and this is the total energy that the system has at the instant 1. So let me call that E. I'm not going to call that E1 because I already know that there is no non-conservative force acting on the system, so E definition will not change. So if I call this E1, the next one E2, and then the next one is E3, well, all of them will be equal to each other. That will be equal to E, the total energy of the system. That means this should be equal to, at the end, it should be equal to the velocity that this particle with 4 kg has, and then the velocity that the 2 kg has. So that should be equal to the kinetic energy at the second instant. Now that would be 1 over 2 m1 v1 squared, and then plus 1 over 2 m2 v2 squared. Initially v1 was equal to 0 and v2 was equal to 0 because it started this motion from rest. And at this instant, the potential energy, this is the first instant, let me call it, this is our first condition, initial condition, this is our second condition. This is this condition just before this second particle with 2 kg hits this spring. Therefore, the spring doesn't have any influence in this equation at the moment. And as you can see, now we have this total energy written in two ways, at the initial condition and in the final condition, and they should be equal to each other, again, because the non-existence of the non-conservative forces acting on the system. Now, V1 and V2 are not independent from each other. They are connected to the same beam. So if we say at that instant where they become horizontal, the angular velocity is omega, then you can calculate V1 with respect to omega and say this is omega times 0.3, because that's the momentum, right? So linear velocity will be calculated by omega r. R is 0.3 here. For V2, it's will be a little bit larger because the arm is a little bit longer, 0.45. Therefore, oops, I have to write this out. This is 0.45. That's it. Therefore, we can implement this information into this equation. H1 and H2 can be calculated, as H1 would be, again, the vertical distance, so we need to make use of trigonometry here. That will be 0.3 times the sine of theta, right? Similarly, you can calculate H2. I'm not going to write that out. Probably have it in the solution. So there we have all the information available for us. In the right-hand side, on the right-hand side, now instead of having two unknowns as V1 and V2, now we have decreased the number of unknowns to 1, which is omega. Okay? So as soon as we can calculate omega, one equation, one unknown, then you can calculate V1 and V2 if you like. And this is the first part of the question. So this is how you can calculate the velocity of any particle at that instant. Now the second part of the question asks us about the maximum compression x of the spring. And there's an assumption here. X is so small, so the position of the rod when the spring is compressed is essentially horizontal. That means, yes, it's going to be compressed a little bit, but then in terms of the gravity, it's not going to have an effect in the potential energy that much, so it is negligible. That means at that third instant, the total energy, because again, we don't have any non-conservative forces acting on the system, at this third instant, the total energy will be transferred into this elastic potential energy. Because when the compression is at maximum, the velocity of the system should be at zero. That is the instant when you push the spring to the end, and then that's the maximum compression you can have. And later than that, it's just gonna extend back, and then you're gonna have a velocity in the negative direction. But at the maximum compression, the velocity is equal to zero. And then this assumption says that we can neglect the change in the potential energy due to this small change in the compression or the length that will be compressed. Therefore, this energy will be transferred totally to 1 over k x squared. That's it. And then you are able to calculate this x from here, and that was what is asked. And the k is already given to you, I hope. Yes, it's given as 35 kilonewtons per meter. So the amount of deflection will be very small. Now, if you had to include the x in terms of, let's say, the potential energy change, then x will be the amount of distance that will be covered in this direction. Okay, so this 2 kilogram mass will go up x units. That means we're gonna store some potential energy, mg. This is m2, by the way, not mg, but m2 g x, right? But then at that instant, the 4 kilogram mass will drop a little bit. Now, this is not asked in the question, okay? We're just saying that if this assumption doesn't hold, if we have a larger x that we cannot neglect. In that case, this is not equal to x, but it is related to x. How is that related to x? This is x times 0.3 over 0.45. Okay, let's call this x1. And now we're going to have a negative sign here, and the reason for negative sign is this is dropping down, right? So it's releasing the energy. So with the negative sign, we're going to have, oops, let me try one more time. M1 G x1. That's it. If this assumption doesn't hold, then you can make use of this equation, and this is our third case. This is our third case, the third condition for this system. obviously, if you want to do, this is our third case. If you want to investigate any further, then what's going to happen at the fourth instant is that this spring will be released and the system will start moving in the opposite direction with the same type of energy. The energy will not change. We don't have any external non-conservative forces acting on the system. So it's going to keep on moving back and forth. We're going to talk about the next example in the next video.